It's possible to make enolates from a number of different functional groups, including aldehydes, ketones, esters, and even carboxylic acids. Note that this means that aldehydes 3 pKa units lower than ketones are about 1,000 times easier to form, and an ester with a pKa value 7 units higher than a ketone is approximately 10 million times more difficult to form than the enolate of a ketone. This is an important consideration for several reasons. One would be as an exercise in comparing acid strengths, which we did in the last unit. Another will be to consider which of several compounds makes the best enolate. And we'll get to this when we talk about the reactions or so-called mixed condensations. And finally, we might use it as a consideration of which base to use in a reaction, depending on how much of the enolate we want to have present. Now, for example, if we keep in mind that the pKa of water, in organic solutions at least, is about 16, that means if we use hydroxide as a base with an aldehyde, that our Ka value, or rather our Keq value, of the equilibrium between the enolate, which we'll go ahead and draw in the carbon anion form, is going to be about 1, which means that we'd have, under equal molar amounts of base and aldehyde, we'd have a roughly 1-to-1 mixture of the enolate and the aldehyde itself. If we did that same exercise with a ketone, however, what we'll find is that the K is roughly 1/1,000, meaning that we're actually making very little of the ketone enolate. So if we put a ketone and an aldehyde together or threw a base in, which one do you think you'd get more enolate of? That's right. If we had an aldehyde and a ketone present, the aldehyde would be the one to make the enolate. Now let's also point out one important thing here, which is that the beta dicarbonyl systems, let's say like 2,4-pentane dione, are considerably more acidic than their single carbonyl counterparts. And if we look at the conjugate base, we can imagine why. Let's think about that as the carbon anion form. Why would this one be so much more stable than the conjugate base of, say, 3-pentanone? You guessed it, that conjugate base is stabilized by not just one, but 2 additional resonance forms, which can delocalize that negative charge onto the oxygens. So whereas the ketone's enolate or the aldehyde's enolate is sharing the negative with a single oxygen, one of these systems is sharing it with 2 oxygens. Let's consider a practical question of ranking relative acid strengths. See if you can rank these 4 compounds in order from most acidic to least acidic. Well, in this case, we'd want to consider what functional groups we have present and how those fit into the relative order of making enolates. And we'll note that we have in the top one an ester with a single carbonyl. In the second one, we have an opportunity to take advantage of the resonance stabilization of two carbonyl groups in this diketone. In this one, we have a carboxylic acid. And in the last case, we have a ketone and an aldehyde. And our rank order is going to be as follows. The most acidic compound is actually the carboxylic acid, not because of its alpha hydrogen, but because of the carboxylic acid hydrogen. Carboxylic acid hydrogens are going to be far more acidic than any of the carbonyls alpha hydrogens, and that's a pKa of somewhere around 4.5, 4.7 for acetic acid specifically. The next case will be a tie between the diketone and the ketoaldehyde. We think about an aldehyde being more acidic or more easily forming an enolate than a ketone, then the one that has one aldehyde and one ketone group is going to beat something that has two ketones. And so this is going to form an enolate more readily than the diketone, which in turn will form an enolate more readily than the ester, which has a single carbonyl compound. So another example we might consider is given a pair of carbonyl containing compounds, which makes the enolate faster or to a greater extent. So if we put each of these pair of carbonyl containing compounds into a reaction together and added some base, which one would be more likely to have more enolate present at equilibrium? See if you can figure it out. If we consider on this side, we have a ketone group. And on the right-hand side, we've got an aldehyde. We know aldehydes form enolates better, so that one is going to be the one that will make the better enolate. In this next pair, similar situation. We have a ketone, we have an aldehyde. But notice that this aldehyde has no alpha H's, and so it's what we would call a blocked aldehyde. It cannot make an enolate because to make an enolate, you have to give up an alpha hydrogen. If you have no alpha hydrogen, no enolate. So in this case, the ketone would actually be the only one that could possibly make an enolate. When we consider an aldehyde versus an ester, then the aldehyde again is going to make the enolate more readily than the ester will. However, if we consider an aldehyde and a beta diester, or we can take advantage of resonance on both sides, even though the aldehyde functional group forms an enolate much more readily than an ester. And notice that's by a power of 10 to the 10th or 10 billion times better. When we add that second carbonyl group, that effect is still going to overwhelm that. In this case, it's actually not by much. So the pKa of this aldehyde is around 16. The pKa of this diester is about 13. It's only a difference of 3 pKa units, but remember That means a difference in acidity of about 1,000.